So what it looks like to me, we already have our constant function, we already have our quadratic function. The next logical piece to complete this might be a linear function, because it doesn't really look like it would be quadratic until up here. So if I did a linear function, in order to find the slope of that line that would make this function differentiable at this point right here. So right now in this video, we're concentrating on this breaking point because we already have this piece of the graph and I need to connect a linear function to it such that it's differentiable at that point. The nice thing about a linear function is that it has the same slope always. And so in order to find how to make it differentiable, all I need to do is figure out what is the slope. So I'll use m for slope. I want to know what is the slope of this quadratic function at this breaking point. So if I know the slope of this quadratic function at that breaking point, then I'll know whatever slope I need for this linear function. So let's come back up here. The nice thing about using Desmos is that it can kind of do it for you. So this is why I like to name my functions, because I can use the names of the functions in order to figure out what these different points are. So first of all, notice that we stopped our quadratic function at the point 1, 4. So the x value that our breaking point is located at is going to be at this point 1. So if I want to know, hey, what's the slope of this quadratic function at 1, you could do it by hand, it's probably not that hard, or when it gets more difficult, because you'll see that as we start to connect more functions, it does get more difficult. When it does get more difficult, you can just type in c prime of 1. I say, hey, what's the slope at 1? Hey, it's right here. C prime of 1 is equal to 2. So that means if I'm going to connect a linear function to this quadratic, I need to connect a line that has a slope of 2. Now, again, when you get into the more complicated functions, you might have a decimal value. The slope might be a decimal value. And in that case, as long as you approximate to 3 decimal places, that's good enough for me. So if this was 2.74924 I could just say 2.749, and then that would be it. You don't need any more. So let's create another equation, a linear function. We're going to call this one d of x, the next one down the line, equals, I know this is a linear function, and I know it's a slope of 2. Now, I can be smart about this, because if I'm smart about it, then I don't have to guess what the y-intercept is, right? If I just go straight into slope-intercept form, I have 2x plus some number, right? And you can see over here, like, how do I connect this to that? And I can start guessing, like, is it plus 1? Oh, no, it's not plus 1. Is it plus 2? Oh, is it plus 2? Oh, yeah, it might be plus 2. It actually kind of looks like that. However, if it wasn't so easy to figure out that it was plus 2, a better way and a smarter way to do that might be to look at point slope form. So if we come back down here again, I know this point is 1, 4. And I know that my slope needs to be 2 at that point. So if you write an equation with point slope form for that, it would be really easy to enter it in and you wouldn't have to worry about it at all. So if we said, we're calling this function d of x, so we can say that's like our y value. So y minus y1, which is 4, equals m, which is 2, times x minus x1, which is 1 in this case. So if we enter that in, it should be the same line, but we don't have to guess this time about what it should be. We know it needs to go through the point 14 in order to make it continuous, and we know it has to have a slope of 2 in order to make it differentiable. So let's see what happens when we enter that in. You can enter in the minus 4 on the same side as d of x, or you can just move it to the other side and say plus 4 on the other side. So let's do that. So that's 2 times x minus 1, and then I'm going to add on that plus 4 at the end. And notice that, yes, it was that same value that it was supposed to be, but this was the mathematical way of figuring it out. So let's restrict that domain. I don't want it to be less than 1, so 1 is my lower bound. So 1 has to be less than x. And then again, you can stop it wherever you want to stop it. So I think I'll stop mine at 3. So less than or equal to 3, and it stops it right here. All right, perfect. In the next video, we are going to connect one more function. I'll show you how to connect one more function before I let you guys try more on your own.